So we talked about unfiltered, unregulated power supplies. And so that would be, and we talked about full wave and half wave. And some of y'all are still not dividing, on the full wave center tap, you're still not dividing your peak voltage by 2. I noticed that too. I did that. But that, okay, but you see on mine, if you see any circles, that means you got it right. I didn't count it wrong because you missed, but you should have missed the one before that, if that makes sense. But you put it in the formula. So far we talked about, unregulated, unfiltered. We talked about unregulated, unfiltered. Unfiltered power supplies. And then we talked about unregulated filtered power supplies. And so the normal progression would be talked about regulated power supplies. And this is what we power do. This is what we use it for. So we use unregulated power supplies, unfiltered power supplies to run basically resistive loads like lights, battery chargers. So battery chargers are usually unfiltered power supplies. So if you ever hook up an oscilloscope to your battery charger, you would see probably full wave. Then unregulated, unfiltered, these are used anytime where the output voltage is not critical. And of course, what happens as we move up the chain, what happens is this cost goes up for the power supply. So I don't know if y'all have ever had to buy one of these yet or not. These are very, very expensive. The ones for your cell phone are pretty reasonable now, but they used to be pretty expensive too. But there's so many people making them. The power supply, so what we mean by regulation is the power supply maintains a relatively constant output. Now we have current regulated power supplies and we have voltage regulated power supplies. So we're looking at a voltage regulated power supply. Your meter has a current regulated power supply. So what it does is this is the way it measures resistance. It comes up there and puts out a constant current, and it steps up and it tries to put out a constant current, and what it does is it steps the voltage up until that current runs. Lithium batteries are current charged. So what we do is we put a constant current into them for a certain amount of time. So that's the way we charge lithium batteries, NiCad batteries. These are all current charged. We put a current. So those power supplies are constant current supplies. The power supply maintains a relative constant output with a changing input voltage and a changing load current. And of course, I just put this so it's not going to be on the. So we're going to deal with voltage regulation. Oops. But it's only if the input and the load current are within certain limits. So everything's got limits, right? You understand that? And as long as you're within the current limit, then there's a high probability that we won't have problems. For percent regulation, this is percentage between the desired regulated voltage and the actual regulated voltage. So it's going to vary a little bit. And the example I use is a speed control on your car. So if you go up a hill, like on 157, now it's 4 lane, but it used to be 2 lane. And there was the big trucks, they would fill up. They had a gas station down at the bottom where the trucks would fill up because they'd start up that hill. And some of them, all the gas would go back into the back of the tank. And you'd see trucks on the side of the road all the time up there because they run out of gas even though they had. and they did have a, that was, the only part of 157. It's mostly 4 lane now, but, going up to Florence, that, had a truck lane on it. So going up that hill, because them suckers would be going 5 miles an hour because it's so steep. But if you was doing your speed control, you started up that hill, then it would actually drop, because what you did is you hit the limits of what your speed control is. So this is the basic makeup we looked at. We know what the transformer does. So we have to choose a transformer. So the transformer has to be chosen to provide the voltage, the desired voltage out here. So we need to make sure we have a transformer that can provide the current that the power supply is supposed to. So what sets the size of the transformer? The voltage, or what type of power supply you're trying to build. Then the rectifier. What does the rectifier do? It's going to convert the AC into pulsating DC. Then the filter. By the way, as soon as we add the filter, we won't see the pulsating DC, even though that's what the rectifiers do. The filter converts pulsating DC into unregulated DC. And then the regulator converts unregulated DC into regulated DC. This is basically what we call a linear power supply. It's laid out really simple as far as electronics goes. It might be not simple to use, but power supplies are easy. What's that first part? Yeah, so what we do is, what establishes the transformer is what voltage and what current what load you're going to run. So as soon as we know this, then we can size the transformer. So I'm not going to go out there and buy a transformer that puts out 50 volts peak peak if I only need 5 volts regulated DC. In fact, that would make the regulator really, really, really work. No, that's this right here. So this is pulsating DC. So this is what we'd get for halfway. Well, almost a straight line. We looked at that. And if I don't, my touch screen got turned on. Sorry. So then we have, this would be half wave. This right here would be full wave. Then the filters are going to take the full wave, and this would be 0 volts. If I can get this drawn straight, Rich. But this is 0 volts. So this is 0 volts right here. So pulsating DC actually means it is pulsing to 0 volts. What happens on unregulated is we put that filter in there, and we end up with this. So this is 0. Now the problem is that this varies with current. Which means the output voltage varies with the load. So the more current's required, so our filters are providing. So what's happening is we charge up our filters, and then the filter provides the load here. Then we charge up our filters, and the filter supplies the load. Yeah, the unregulated with the ripple across the top. Over here, what we do is our regulators are going to operate down in here. So what they're going to do is they're going to clip off that top. So if this goes up to, let's say, 10 volts, and it drops down to 8 volts, and our regulator is set to regulate at 5 volts, then we'll get a constant output. And what it does, it just lets the DC pass through, as long as this guy right here don't what. So if you come over here and you start loading this thing down, and now all of a sudden these things do like this, then you're going out of regulation. So, and this is determined by the current. So this right here is, this black one right here, this is bad. But so that's when you're trying to get too much current out of the power. So if you try to get too much current out of the power supply than what it's designed for, then it goes out of regulation. If you come over here and we're looking at, if we're looking at 120 volts plus or minus 10%, and you get 20% on that, out of 20% out of tolerance, then the thing is going to go out of regulation. Because it's not giving enough up here for the filter. So what's happening is that you'll drop down into here. So if the input voltage drops, we drop down into here, right? So let's say the input voltage drops. Then my capacitor is going to come over here and still going to do the same thing, but now we're over here into our regulated voltage. So what we're saying is that your regulator is going to be able to regulate over a certain percentage of change on the input voltage and a certain percentage of change on the output current. If you exceed any of those, then the regulator can't regulate it. And that's like going up the hill on 157. Or going up the hill on 19th Street in Bedford. Ever been up the hill at 19th Street in Bedford? Some of y'all have. This is a deep hill. And if you had your cruise control engaged like 40 miles an hour and you start up that hill, there ain't no way in the world that car is going to, that engine's going to maintain 40 miles an hour. I just added these before class started. If you're looking at my post, but I'll upload the new version. You wouldn't hear what I told the class that. I pulled this out of a previous slide that we had, and this is the one model that we put up several times. And this is a linear power supply, very easy to troubleshoot. You know, if I was to come over here and actually look at the power supplies on the trainer. So this is the power supplies on the trainer, and we can trace it through. So here's my transformer. It's a multi-winding transformer. This comes over, there's a full wave bridge, there's my filter. Comes over here, so there's the filter. So here's the input, here's the transformer, here's Alabama Power, or TVA here. Comes to a full wave bridge rectifier. There's my filter. It's 4,700 microfarads at 16 volts. Then it comes over here, there's the regulator right there. Here's the light that comes on. This is the 5 volt regulator. So here's the little terminal that you connect up to right there, 5 volts. And here's the LED that comes on 5 volts. Very simple. So it means if this guy wasn't working, if this light right here wasn't working, and I came over here and I had 10 volts worth of unregulated DC, and it wasn't working over here, then right off the bat I'd know my regulator is going out. That's how simple it is to troubleshoot. If I wasn't getting 10 volts right here, then odds are I'd drop back to my bridge rectifier. I would check the output of my transformer. We've had 2 transformers go bad on our trainers. We got spares. But all we did was check the output of our power supply. So you come over here and you need 10 volts DC right there, and over here you're measuring, 3 volts RMS, then odds are you got problems with the transformer. So this is what's nice about linear power supplies. They're pretty easy to troubleshoot. And this used to bother me. We had instructors that have one of these trainers that go bad. The power supply would go bad, and they'd get a permanent marker and write up on their bad. When we could do what? We teach these classes, and we can fix them, right? Y'all could probably, with very little training, you could check these power supplies, and you could fix them without any problem. This is a little more complicated, but we'll talk about it when we get in more detail. But here's the regulator. This is the 12 volt regulator, and these are your variable regulators right here. So here's the plus 12 volt regulator. Here's the minus 12 volt regulator. Here's the variable power supplies. One of them's minus, one of them's plus. This looks like it's a full wave bridge, but it's actually full wave center tap. We'll talk about that when we get there. So they don't have any half waves inside this thing. Both of the rectifiers. But rectifier, filter, regulator, output. And then of course, these guys have to, the 3-terminal regulators have to have what we call pre-filters and post-filters. Because they're trying to switch all the time to maintain the constant output. So that's the power, that's the trainer's power supply. And it follows what? It follows directly with this line right there. Exactly. Transformer, rectifier, filter, regulator. This is so what we're going to do is we're going to look at just about the basics, and you're going to run into these, and I can actually show you all right off the bat where some of these are being used. This is the basic VI characteristic curve that you're doing in lab, I think it's 31. So what we did the other class is we did this side over here. So we broke over right around, I think it's around 100 volts. We broke over. And then this over here, you're going to do this side, and that's where you're going to set up the circuit. Remember, you're going to use the potentiometer. By the way, guys, if you get something out of this cabinet, when you get through, you need to do what? Put it back. So there was a trainer left out after y'all's class last time, and somebody left all their probes out on the table. So when you get them out, you need to put them back, please. So if you don't do that, then I know where y'all sit now, so I'll just start taking off points for not following instructions. Because you don't want to create more work for your boss, right? If you create more work for your boss, then odds are he's not going to be your boss very long. Right? All I can do here is I can just take off the grade. So this is the breakdown for a typical diode. This is where we want it to operate at when it's forward biased, and we never, ever, ever, ever want to exceed this voltage rating, because if the diode breaks over, that's going to give us a problem, right? So this is a symbol of a diode. It's got a different symbol. This is a symbol of a diode referred to as a Zener diode. And most people, if you put that in a word processor, they'll probably say it's spelled wrong. But this is a Zener diode. So instead of having a straight line, he's got these little things right here, telling us that this is a Zener diode. Okay, now this is at the end. We kind of jumped on chapter, I think it's chapter 6 in the book, where they talk about regular diodes, and they get into special diodes, and then they get into power supplies. What I'm trying to do is follow this block diagram. And so as soon as we got through with diodes, we went into rectifiers. So we jumped into chapter. Zener diodes, I think, is covered in chapter 6 in the textbook. And these are the basics for voltage regulator. This is a voltage regulator. So a silicon diode, so Zener diode is always silicon. Zener diode, a Zener diode is specifically designed to operate in the reverse breakdown region. So we reverse bias each other. If you forward bias them, they act like a diode, and you might as well use the diode. Because these are what we'll call, the next slide shows. So what we do is, now we're going to protect this thing, and we'll talk about that in a minute. So what we're talking about on the Zener, if I come over here and I take a Zener, now what I'm going to do right now is I'm going to put a resistor right here because it wouldn't work. In fact, the Zener would burn up. And then we come over and put a Zener right here. And then we'll put a common. And then I'm going to put my output voltage over here. And over here I'm going to start, let's say we're going to start with a variable power supply. We'll call this RS for a minute. Let's say, now, the Zener diodes, usually the breakover voltage is a lot lower than regular diodes. So let's say the breakover voltage was 5 volts. Well, let's say we start off with 1 volt. Well, since this guy is not broke over, then we would have 1 volt out. Then we go up to 2 volts. This guy is not still above its breakover, we'd have 2 volts. And these are plus by the way. 3 volts, 3 volts, 4 volts, 4 volts, 5 volts, 5 volts, 6 volts. Well, now the diode's going to break over. So what happens is it came down here, and all of a sudden the diode broke over. Now what's going to happen is this guy is going to try to always drop 5 volts. So according to Kirchhoff's law, this is a series loop. It means as soon as this thing breaks over at 6 volts, this guy right here is going to drop 1 volt. So the sum has to equal, right? You understand? Okay, what if this goes to 7 volts? Well, the diode broke over. So it's going to try to keep dropping 5 volts, and this resistor now will go up 2. So it's the sum of the voltage. So what's happening is the Zener is going to try to maintain the breakover voltage. And then the resistor is required. If I didn't have that resistor, as soon as I put 6 volts on there, that Zener would have been gone. Because as soon as this thing breaks over, it acts like a closed switch. But what it's trying to do, it's going to try to maintain a constant output. Which means if I was to come over here and put, let's say, put a light bulb right there, it would always see about 5 volts. So anything in parallel that I put in parallel with the Zener, it's going to try to stay at that Zener voltage, by the way. The breakover voltage, we don't call it the breakover voltage, we call it VZ. So the Zener is going to try to regulate around VZ. Now it's not perfect because the Zener has an R component. So what happens is the more current we put across it, the more it's going to drop. So up here, this might be, it might break over or start this. This might be 4 volts. And then this right here in the center, this might be 5 volts. And this down here might be 6 volts.
You said that, this diode always puts out 5 volts. Now, what's coming in at 7 volts, says that the resistor goes at
Well, you're not saying will be added. It's going to drop. So what's going to happen is this guy right here, it's going to drop the difference between the under and under voltage. And the regular voltage. It's in there for that purpose. But notice the Zener is reverse bias. So Zeners operate in a circuit reverse bias. If you forward bias it, it's going to drop around 7/10 of a volt. If you check it with your diode, it's going to check just like a regular diode. So if you check it with your diode checker on your meter. So just because it checks like a diode don't mean it's not a Zener. So this is where it's going to be very important to find that part number on it. Or look at the schematic and see what it is.
Is it always, the Zener is always going to reverse bias position, or does it go forward and reverse at times?
It can, but if you forward bias it, and I'm sure there's applications where they do that, but the main thing is the main thing of this guy is, and if a diode, if something will do something, this bothers me. They in data sheets for digital devices, they talk about some input would be invalid, and I tell them that's not true. Some engineer, if it's got 16 combinations you can put on that input, some engineer is going to find a use for all 16 of them. So normally, 99% of the time, we never operate this thing forward bias. But to say we will never see it, Janice, I mean, you get an engineer out there and he wants to clip off one side and pass another, then that would be perfectly legal. Because it's not, if you forward bias it, it's not going to damage the bias. It's going to act like a diode. If you forward bias it, it's silicon, which means it's going to drop about 7/10 of a volt. But notice the big difference. The breakover voltage for Zeners are usually a lot less than the breakover voltage for, so the one in 914, I think its breakover voltage was 90 volts. So standard diodes, switching diodes, and of course rectifier diodes are going to have high breakover voltage. Zeners are usually going to have low breakover voltage because they're designed to operate on devices that we usually run off of DC. Any more questions? Good questions, guys. And yeah, Janice would say, will we never forward bias this? Will the engineer never forward bias this? That's highly unlikely because it don't. I mean, I'm sorry. That's highly likely that some engineer will find you across the resistor. Yeah, because what we're doing, and we call that the series dropping resistor. Now, it's going to have a bunch of names, but generically, we're going to call that RS, for series dropping resistor. But if you're looking at a schematic, it might be, R10 or R15. It's just for formulas. If we come up here and we establish a standard, it makes it easier for us to do formulas. So, I mean, if I came over here and put, of course, we might not do this, but if I was to come over here and put 10 volts, this guy's dropping 5, I'm putting 10 volts right there, what's the resistor got to drop? It's got to drop 5 volts because of Kirchhoff's voltage law, right? Understand? But what's happening is this guy right here is staying fairly constant. Is it constant? No, it's not perfect. But if we come over here and we can regulate around in here, it's going to be really, really good. So as soon as sizing this resistor is very critical. If you choose a resistor too big, so let's say this guy over here needs 100 milliamps, and I come over here and I use a 10K resistor, or even a 1K. Well, let's say 10 milliamps, 1K. That sucker's going to try to drop 10 volts. And I'm only applying 10 volts. So that means I chose the wrong resistor. So choosing that resistor is pretty important. What's R equal to? Ohm's law. Y'all need to practice that. That in electronics, that's about saying, that's almost as important as saying, what's your name? Yeah, VOI. So we'll solve for that resistor using that formula right there. I mean, we'll just have to figure out what V we're going to use and what I. So the book doesn't bring that resistor in right now, but I tell you, it's got to be in there. because it's going to take unregulated. We got to have more regulated than we have regulated, right? You understand that? So we're going to have to drop some volts. So RS is required. But whatever I put in parallel with the Zener is going to see Zener voltage. Is it going to vary with load? Yes, it's going to vary with load, but it's going to be very, very low. In fact, one of the labs will do. Two types of breakover. We know avalanche, which is bad. This is what we're looking for in regular diodes. And then Zener. Zener breakdown occurs at low reverse voltages. Zeners have a very narrow depletion region, which we don't need to know. As the reverse bias is increased, the reverse current remains very small until it reaches the knee of the curve. Breakdown effect begins at the knee. At this point, the current increases rapidly. The breakdown voltage remains essentially constant. The Zener diode keeps an almost constant voltage across its terminals within a certain current range. So we have right here, this is called IZK. That's where the thing actually starts breaking over. And then down here somewhere we have what we call IZ max. That's where the Zener burns up. So as long as you operate this thing, we got to operate it above the knee, right? Or past the knee, probably would be a better term. And we got to operate it below IZ max, Zener current max, because it's dropping the voltage. And we know if we put current to a voltage, we get watts. And if you exceed the wattage rating of the Zener, then you're going to burn it. So when I decide what loads my Zener is going to run, then these two ratings right here are going to be very important. IZ max, IZK. So IZK, this is the current that flows when it originally breaks over. And then the IZ max is the maximum current that you can get through it before it burns up. Are we okay? So this is the characteristic curve. We're not looking at the forward characteristic. All we're looking at is the Zener side. So we have a current that in the data sheet. This is called IZT for Zener test current. So this is going to be in the data current. This is usually about halfway between IZK and IZ max. So if we operate it on this side, then the Zener goes out of regulation. As soon as we get right here, then the Zener is actually in regulation, so it's regulated. Here, IZT, this is about in the center of IZK and IZ max. If we operate it above this, then there's no guarantee that the Zener won't burn up. Are we okay? Any questions so far? IZK, the regulator Zener must always operate above or more than this current. IZT, this is the current flow where VZ is established. The circuit should be designed to regulate as close to this current as possible. IZ max operating above this current will damage. I shouldn't say will, it may damage it. I think the analogy I use is that like the tach gauge on a car. As soon as you go past the red line, it don't mean your engine's going to burn up or blow up or overspeed. It just means it's not guaranteed to blow up anymore, right? Or burn. So if you operate it above IZ max, it probably will be damaged or may be damaged. This current is not given on data sheets, but one thing they do give you is they give you the maximum power and you have the Zener voltage. So the way we calculate IZ max is we look on our data sheet and we find the power rating of the Zener, PZ max, and then we divide that by the Zener voltage. So here we're taking this formula, power is equal to V times I, and we're transposing it to solve for I. That's not a T, that's a Z. So IZ max is not given. You have to calculate it. Are we okay? Data sheet? Yeah. It's just that IZK is going to be given on the data sheet. IZT is going to be given on the data sheet. IZM is not given on the data sheet. But they give you the power that the Zener can the power that the Zener is rated. Any more questions? Any questions, yeah. So yeah, you got a whole formula sheet section on Zeners in there. Right, Mario? I said you got a ideal. So equivalent circuit, Zener is equivalent to a voltage source. Practical, Zener is equivalent to a voltage source in series with a very small resistor. The Zener impedance can be used to calculate the change in voltage by the change in current. Now, Zener impedance is okay if we're not going to worry about that because we're going to design it and we're going to understand that regulation is not going to be perfect. If I was going to calculate exactly what voltage would occur at what current, then I would need to know the Zener impedance. But we're not going to use that in any of our calculations. So we're going to figure out how to size that resistor. We're going to figure out what currents the Zener can handle before we burn it up. And then we're going to put that Zener in there, and we're going to understand that if it's a 5-volt regulator, it's not going to regulate at exactly 5 volts. It's going to vary slightly with load. I think ours, when we design it, I think ours regulates with about 2%. So that's really good regulation, 2%. We look at some of these guys, they regulate less than 1%. So these guys are really, really good. That's one reason they cost so much money. So basically, this is the model we're going to use. We're going to use ideal characteristic curve. So we're going to assume that when that sucker breaks over, it's going to maintain a constant output for our design. And then we're going to understand that it's not going to be perfect. It's just like if I had to, and engineers understand this, so resistors are not made in infinite quantities. They have what we call a set of standard resistors. And we're going to use that for our calculation. So when we calculate a resistor, we might come up and get 122.35 ohms. Well, the problem is they don't make 125.235 ohms. So we're going to figure out, okay, what do we need to do? Do we need to round that up, or do we need to round that down? We're going to have to figure out that, huh? And we're going to compensate for that too. So we got to compensate for that too. So we're going to say, okay, one thing nice about this is we'll look at that. We always want more current flow through the Zeners than what we calculate. So our resistors will always run down. I'm sorry, always run down. On Zener. On the Zener power supply, they always run down. Then Mario will check the tolerance. If the tolerance is not within what we want, we'll go down to the next 10%. So we keep going down on things. That's really good. So yeah, we do have to do that. R is equal to 0 by. So this is where we're going to say it's going to regulate at. So we're going to regulate somewhere. So this is showing you, I don't know if this is in your textbook or not. This is showing you how they calculate the Zener impedance. So they measure VZ, they measure IZ, RZ. By the way, in AC, and we need to go ahead and talk about this. In AC, we have devices called inductors and capacitors. This creates something called reactance. So normally, if we've got capacitors or reactive devices and non-reactive reactive circuits, it does not create at all. It creates what we call reactance. If we combine reactance and resistive devices, technically that is not R, that is what we refer to as impedance. Unfortunately, that is a term that you're going to run into a lot. So in your mind, you need to say impedance and resistance are basically the same, even though technically they're not. So here we have a change. So here we're having a change. So they're taking that change to be an AC problem. Instead of calling it Zener resistance, they're calling it impedance because of the change. So be careful with that. So in AC, most of the opposition in an AC, people are going to call it instead of what? Instead of resistance. So since we have a change here, so since it can vary, they call this Zener impedance. And in formulas, we represent impedance with the letter Z. And what unit is it measured in? Yeah, all opposition in a circuit is measured in ohms. And this gets people in DC confused a little bit. So reactance is in ohms, impedance is in ohms. So saying ohms is, so technically when they teach you that ohms is the resistance in a circuit, that's not true. So ohms is the opposition in a circuit, the opposition to current. So this is basically how this would be calculated. But like I said, we don't have to calculate it. If we need it, we use it. So data sheets, they're going to show us our impedance. They're going to show us the temperature range that these guys are designed to operate in. They're going to give us our power dissipation. And then they're going to give us a dirating factor that we do for temperature. They're going to give us a Zener test current. They're going to give us a Zener current. They are not going to give us Zener max. IZ max. You'll have to calculate that. Are we okay? They got any problem? So let's come over and get one of our data books. Social distance, right? You need to say again? Yeah, me too. We need to take a little break there. In fact, I just got a throat fingernail. Somewhere in this thing, you got a 1 in 47, 1 in 47, 0 something. It's actually a range. Yeah, 1 in 47. Oh, that's neat. I never use it. So actually, it goes from 1 in 40, my data sheet goes from 1 in 4728 up to 1 in 4784. So you're looking at 1 in 47. It sure turned a lot of pages. I would have thought it would be towards the front. So mine is on this one, it's on like the third or fourth page. Right after the 1 in 48, 1 in 47, 28, 1 in 47. So it might not look like mine. Like I said, mine is Fairchild. This is Motorola. So mine's made by two different companies. So this is a 1 watt electrically sealed glass silicon sensor battery. So there's your wattage rating up there. So all these are 1 watt sensors. Okay? A maximum rating, maximum wattage would be 1 watt. Operating temperature, we can operate this thing anywhere between 65 and 200 degrees temperature. Then on the sheet, it says, and by the way, don't mark in my database. If somebody's got E marked in my database. So, what we're saying is that these are our zingers. So this is a 4728. It's got a VZ of 3.3. A 4729 is 3.6. A 4730 is 3.9, 4.3. But the only thing that's basically changing is our Zener voltage. So here's our Zener voltage, VZ. Are we okay? Here's the Zener test current. Here's IZK. So that's the knee current, which we're going to look at. And so what would IZ max be for a 1 in 4732?
What you on that?
Oh. Huh? I hear Mario, he jumped right on that. I said, you jumped right on that. So it's a 1 watt Zener. It's rated at it's rated at 4.7 volts. On the front page. I just read it to you. Then the front page. Right into the description. First bullet. 1 watt electrically sealed glass silicon Zener die. See where I read that? Oh, I'm sorry. Right here. It's not. Yeah, it's not on this one. It is on y'all's. I don't think. Maximum ratings. Yeah. So right here, maximum ratings. I tried to blow this up as much as I could, but 1 watt. So what would the maximum? What would IZ max be for a 1 in 4732? This would equal 1 divided by 4.7. Yes. So that means if I tried to operate this diode and tried to get 213 milliamps to flow through the Zener, then it could burn it up. Well, what they try to do is anything they can leave out, they're going to leave out. So they take for granted you should, if you're going to design these things or work with these things, you should know that. So that would be, giving you instructions on how to use a brake pedal in a car that you just bought. They take for granted you won't. They'll show you the location of the brake pedal, but they don't show you how to use it. Or they show you the location of the steering wheel, but they don't show you how to use it. So it's just like in that car, the manual you get in the car. If you buy the car, they take for granted you already know. So this is the diode that we'll be working with, 1N47 series. So these guys has a breakover voltage. The minimum breakover voltage we can get the Zener voltage would be 3.3, and then the maximum we would get would be all the way up to 100 volts. So 1N4764 on my chart says it's 100 volts. Oops. And that's the biggest. I've zoomed in as far as I can go. Oops. Yeah, this one's okay, that will. So if all this neat stuff in here, Zener test current, this is where VZ is established. We don't need to know that. We're basically going to, out of this chart, about the only thing we're going to be using is the Zener voltage, the knee current, and then, not this one, this is impedance, IZK. So this is the knee. So we got to make sure we operate it above. So if I'm dealing with the, what's the 5 volt Zener? Oops. I keep trying to move it with this. So 5 volt Zener, 5.1 volt Zener, this is a 1N4723A. What's the A stand for? 5.1. Okay. So we've got to make sure we make at least 1 milliamp flow through that Zener. If you don't make 1 milliamp flow through that Zener, it's not going to be regulated. That's the knee current. If you operate it with less than the knee current, then the Zener goes out of regulation. So we always have to operate it above IZK, and we need to operate it below IZmax. Alright, let's take a 10-minute break. VZ, right? And IZK. And that should be the two things that we need that I can think of. Zener can be used as voltage regulation regulators in low current applications. Oh, 4 voltage regulation. It takes a varying DC unregulated and keeps it at a relatively constant DC output. The Zener can only work over a set of ranges. We have to operate it at a current above IZK. it may damage it. Yeah, it has an operating rate. It's just like the alternator on your car. You ever notice why your car idles at about 1,000 revolutions per minute? Because if you operate it below that, your regulator out of your alternator cannot regulate it because it's not spinning the alternator fast enough. The alternator is not putting out enough voltage to regulate. So I don't know if you ever rode a Harley. That's what I wrecked on my own. We run that speed real low. If you ever looked at the headlights, well, what we're doing is we're below 1,000 RPM while we're at a red light, and the regulator can't regulate anymore. So you ever notice that on this bike? But it sounds good, doesn't it? So, and you pull out the baffles on your exhaust too. So yeah, I got way off. I got off on my motorcycle bike. That's what I was riding, by the way, when I had my motorcycle. It's a total of my Harley. So yeah, if we operated at a current that's lower than the need, so when we design this thing, there's going to have to be current flow through the zener. And we're going to have to figure out how to do that. Above the maximum current, then the zener may be damaged. So in yours, if you look at your slides online, it probably says wheel, but that's not true. So it may be damaged. And the analogy is, like we talked about the tack gauge in the car. So this is not in your textbook, but this is a good example. So here they're showing the input changing, but the output stays not constant, but fairly constant. So here I think it's right here, and here it's right here. And what we're actually doing is seeing the zener impedance. And this is what's really cool. Any voltage applied to the zener that is above K will be above VZK will be a short circuit. So as soon as that thing breaks over, it acts like a short circuit. A resistor that is connected in series with the zener, we will call RS, but in real life it's not going to be called RS. It's going to be called R53 or something like that. It's just that we'll give it a generic name so we can use it in formulas. It's required to drop the difference between the unregulated and the regulated voltage. Calculating the size of this resistor is critical to the operation of the circuit. If we choose a size that's too big, the zener will go out of regulation because you'll be dropping it below IZK. If you choose a resistor that's so small, the zener will probably burn up because you're going to be operating as though IZK. So this is a basic zener positive regulator. So that would be RS. So what we'll do is we'll come over here and just get a feel of what's going on. We'll come over here and we'll connect a resistor over here. This is where we'll connect our load. So right now we'll use a resistor. So this is our load. And we'll say the zener, let's say the zener VZ is equal to 5 volts. And the load requires 100 milliamps. So that's our load. 5 volts and 120 milliamps. We don't care about the size because power supplies are not designed around ohms, it's designed around amps. How many amps can it put out? So if I look here, it says nothing about ohms. If I look at this power supply, it says this guy here can put out 20 volts at 4.5 amps. So if I needed a 20 volt power supply and I didn't pull over 4.5 amps, then I could cut the thing off this, it feeds into my computer and I can use it. I had a chair in my computer room that the power supply went out on. And I've been playing around with these things for years, so I got a whole box full of these power supplies. And I just found one that put out 12 volts. I cut the end off of it, figured out which was positive, minded, hooked up to my chair, and it worked. So yeah, you can use these as power supplies. You got a bunch of these and they're good. Just look at them, see what they're rated at. These are not computer power supplies. These are power supplies. So I got a tendency, when things I've got, if I can't fix them anymore, they're really broke. I can tell you some of the stuff I've done. So what would happen, that means, let's say 5 volts, so let's say we're putting 7 volts over here. Okay, so how much voltage would that resistor have to drop? 2. How much current would I have to flow through my Zener? Well, the Zener, if it's got a knee current of 1 milliamp, then by George, I've got to make at least 1 milliamp flow through the Zener. Got to. Of course, we're going to go above the knee, so odds are, let's say 2 milliamp. So what size resistor would I use up there? And we'll use absolutes now. We're back to DC, guys. Parallel circuit. Sums of the current flow in parallel circuits equals IT. Well, this is IT right there. IT is flowing through the resistor. IT is flowing through the resistor. So that means what I would do is I would try to choose a resistor that's going to, R is equal to V, so it's going to drop 2 volts. And it's going to see, right now it's seeing 102 milliamps. And we're setting at the bare minimum, but we'll look at it in a minute. So what would be the absolute? So I'm using I is equal to V over R. Oh, I'm sorry, R is equal to V over I. Right? So what size resistor would that be? 2 volts at 102 milliamps. So what size would that be? 60 ohms. Okay. So what's going to happen if this input goes up to 8 volts? I didn't get it. Y'all got it. Okay. Y'all need to speak up. Y'all need to speak up. Millions? Okay. And of course, this is just play around. We'll figure how to size this resistor, because it's going to be very critical. So as long as I go up, you'll see we're okay. So what do we got? 19. Oh, okay. I don't know. Well, no, because I'm taking, if you got a fraction on the bottom, so this is actually R divided by 2 over point, right? 102. Well, anytime you divide by a fraction, your answer has got to be bigger than what your top number is. Y'all understand that? And this is what I'm trying, it don't mean it's right. I'm trying to get into your head how you know your answer is wrong. So anytime I divide by a fraction, my answer will always be bigger than that number right there. So right off the bat, if I come up with an answer that's below 2, that's 2 or below, I know that answer has to be wrong, and then it's up to me trying to figure out what I did wrong, right? Now, if I come up with an answer above 2, it could be right, and that's what we're trying to do. It could be right, but if I come up with an answer that's less than 2, then it's definitely wrong. So what do we get? 19.6 ohms? So Louis, you okay? Figured out, yeah. And engineer notation is tricky on those. In fact, a lot of times I can do it faster. I've been in this so long that I see 102 milliamps as 0.1 102 amps, and I'll put that in the calculator without even looking for my scientific notation or for my engineer notation. And it just saves me a little time. Okay, so what we did is we came over here and raised this to 8 volts. So what's going to happen? No, the resist. So you're saying once I design a power supply, I'm going to take this thing apart and keep changing that series resistor depending on the input voltage. No, once we choose a resistor, it's a resistor. So that's a really good point. That's because of what we did before. All we did was choose that resistor under one situation. But now it's got to operate on all situations. It's not going to do it. We'll see what's going to happen in a minute. So I've chose a 19.6 ohm resistor, or let's just call it a 20 ohm resistor. Makes our math a little easier. I've chose that. I put it in my circuit. Now the input goes up to 8 volts. What's going to happen? My load current is 100 milliamps, period. My voltage is not going to change across the load. 100 milliamps, okay? So what's the Zener going to automatically do for me? It's going to try to keep it constant. So this is our first dynamic device that we've actually looked at. If I come over here and look at that, you notice that VZ can actually change. So this guy right here is going to dynamically change its opposition to try to maintain at that voltage. So what that means is I'll come over here and I'll look at this resistor right here and I'll say, what current flow for that 20 ohm resistor to drop 3 volts? Now I'm going to come up there and I'm going to say where am I at? I'm going to say I through RS is equal to V3 divided by 20. So what is I through RS now? I is equal to V over R, right? 150 milliamps. Huh. According to Kirchhoff's current law, it says the sums of the current in a series, in a parallel circuit, has to equal to the total current. Our total current is 150 milliamps. What's got to happen? It's not going to break over because we're talking about amps. We're not talking about volts. This guy right here is going to maintain 5 volts. It's broke over. It's been broke over, and that's why we said 2 milliamps. But what's going to happen? This guy right here is pulling 100 milliamps, period. What's got to happen? Got 150 milliamps flowing right here. I come over here, I got 2 paths. I got 100 milliamps going that way. The sums of them's got to equal to 150 because I got 150 milliamps right here. What's got to happen? What's that? So the current in the Zener would go up to what? 50 milliamps. Well, you say, well, it can't, but it's not a resistor. It is a dynamic device that is going to vary its opposition to maintain try to maintain a constant output. So that Zener technically automatically lowered its opposition to try to maintain 5 volts. Automatically. We didn't do anything. So its VZ has the ability to change. It's not a resistor, it's a Zener. It's a dynamic device. So here we're actually seeing this thing can automatically change its resistance. Well, we got a problem. So let's say we chose 20 ohms. Let's say it drops down to 6 volts. Let's make it a little more dramatic. Let's say it drops down to 5.5. I want to make sure we see our problem. So 5.5, that means this 20 ohm resistor is now dropping what? 0.5 or 500 milli divided by 20. What's my current? What's that? What's the problem? The Zener has no current. Zener goes out of regulation. So this guy right here is going to drop down to 4 or 3 volts. So what we got to do is we got to choose that. So I chose the wrong size for the range of voltages that I needed out there. In fact, let's do 6 volts. So 6 volts means this guy's going to drop 1 volt. Or going by math, it's going to drop 1 volt. So we come over here, we said 1 volt, so I would be equal to V 1 over 20. What's that? 50 milliamps. My load needs 100. So we're going to get 50 milliamps out here, which means the load's not going to drop it, so we're going out of regulator. So what happened? I chose a resistor that was too big. So if you size that resistor wrong, you might be able to regulate up here, but you won't be able to regulate down there. Huh? That's the $100 question. It's got to be a formula. So R is equal to what? V over I. So what we need to do is we need to figure a resistor. So if this goes down, Zener current goes down. If this goes up, Zener current goes up because the resistor's constant. We didn't have any problem with it going up. We had a problem with it going down. Right? Understand that? So if the voltage goes down, so that means up here, we probably need to use the minimum voltage. It's going to come in. Now over here on my current, so let's say I'm changing my load current. And let's go back to our original setup where everything seems to be working all right. So right now to calculate RS, we know we're going to use our what? VN minimum. Because what we're trying to do is we're trying to make the Zener current move in that direction away from the knee. Sorry. We're trying to make our Zener current move go up. Everybody okay? Okay, so let's leave this alone. So this is a 5 volt Zener. And let's say we have, what did we say, 2 milliamps flow. And we're dealing with, what was our voltage? 7 volts. Okay. That means this guy was supposed to drop 2 volts, so we chose the 20 ohm resistor. Actually 19.9. So this guy right here would be dropping 2 volts. So IT would be equal to 2 divided by 20. What'd they give us? What's that? We got problems already. Now, the load was supposed to require 100 milliamps. If the load requires 100 milliamps, then the Zener has no current. So instead of going to 20, I should have went down. So to see how this works, I'm going to come up and change this to 15 ohms. So what would the total current be right now? 100 what? Okay. So what that means is if I come over here and had a load, that gave me 100 milliamps at 5 volts. That means we would have 33 milliamps of Zener current. Everybody okay? That makes sense? Everybody okay? Okay. Well, what's going to happen, and this guy right here is dropping. This guy's a 15 ohm, and it's dropping 2 volts. 15 ohm, dude. So what we're going to do is we're going to leave the input voltage alone. And what we're going to do is we're going to vary the load. So with the load being varied on this thing right here. So my battery's totally dead. And then I plug this thing up. And then my battery's fully charged. Plugs it up. I take my battery out. I run my DVD player. Current goes up. I don't run my DVD player. It don't run. I turn the intensity up on my light bulb. So that would be like saying the load on your battery in your car is constant. Is the load on your battery constant? So you're rolling windows up, you're turning on air conditioner, you're changing temperatures, you're doing all this kind of stuff. You're turning your radio up because you like that song, right? You understand that? And then my wife reaches over and turns it back down, right? So let's look what happens if the load current varies. So let's say the load current goes up to 100 and let's say it goes up to 120 milliamps. Yeah, 120 milliamps. So what's going to happen to Zener current? So the Zener current drops down to what? 13 milliamps. So that means we're moving toward the knee. We don't want to move toward the knee. We want to move away from the knee. So all my things I'm doing, I'm saying VN minimum. So if VN minimum, if VN goes up, Zener current goes up. Right? You understand that? So we're saying, okay, I'm going to take my minimum voltage coming in. Okay, over here, if load current goes up, Zener current goes down. If load current goes down, Zener current goes up. We're looking for something that's going to cause the Zener current to move away from the knee. So we're going to calculate this, VN minimum over I, the load. VN minimum over I, the load maximum. And then plus IZK. So that means if this goes up to its maximum value that we rated at, and if we go ahead and add IZK, we got at least IZK flowing through the Zener. So it always operate below the Zener. And that's the formula right there, guys. Minimum voltage over maximum current plus IZK. If we choose that, then our no, VN is what you said, VN is not in a data sheet. VN is your power supply. So over here, we came through what? We came through this. Okay, we came from the transformer. Who chose the transformer? You did. Okay, we're gonna go through the rectifiers, right? Who designed the rectifier? You did. Then we come over here and we go to the filter. Out of the filter, we get unregulated DC. So this is what we're looking at, unregulated DC. So if I come over here and I do this, and at full load current, this voltage right here. So let's say we're trying to get a 5-volt regulator. Let's say up here it's 7 volts. Down here, the maximum of this server right here would be 6 volts. What minimum voltage would you use? 6. So it's what you get out of your unregulated portion of your power supply depends on your minimum voltage. And that's not going to be on the data sheet, so it's up to your design, right? So you're giving it, the rest of your power supply is giving you this. And right now it's going to be going from 7 volts down to 6. 7 volts I'm not concerned with. As long as it don't exceed the current rating of the Zener, I'm not concerned with it. And we'll have to look at that too. So as the unregulated goes up, Zener current goes up. And we want to make sure we stay below IZ max. So there's more calculations than it looks like. So we have to calculate and make sure we're not going to burn up our Zener. We chose a 15 ohm resistor. What else do I need to know about that resistor besides 15 ohm? Huh? No, we're just talking about a resistor. I'm holding a resistor in my hand. What do I need to know about a resistor before I stick it in a circuit besides ohm? We need to know the tolerance and we need to know the watt. So if I take that 15 ohm resistor and I go out and I find an eighth of a watt in there, I say, oh, this is 15 ohms. I'll stick it in there. I know it's going to burn up just like that. So that's something we got to check. I know I told you the story about the power supplies, right? The students field. They kept burning up 100 ohm resistors. And they wanted to blame it on the power supply. Well, my power supply keeps burning up these resistors. And what was the problem? They was using a quarter watt resistor, putting 30 volts across it. V squared over R. So that's 30 squared over R, right? You understand? They was burning them resistors up left and right. And they thought it was their power supply. But they forgot about that. So when we choose that resistor, we got to think about, once we choose it, first of all, we're going to have to make sure we understand the tolerance, right? You understand that. And then next, we got to make sure that whatever current flow we put through it is not going to be enough to burn the resistor up. Whatever current flow we put through that Zener, we got to make sure it's not going to be enough where we exceed 1 watt. So there's some things you got to consider besides just the math. But if I can size that resistor, if I know my minimum voltage and I know my maximum current, so let's go ahead and size it. So let's say we got an we got a G current IZK of 1 milliamp. And what's the maximum load current you're going to design our power supply around? Oh, go ahead. Let's design it around 120. Let's see what resistor we use. So my minimum input voltage we said was going to drop down to 6. Okay, then I would come over here and I'd say 120 milli plus 1 milli, and then that would be R. Okay. All right. So what I would do then is, let's say 50. If my resistance goes up, my Zener current goes down. So on Zeners, we never round up. We always round down. But that's not even very important anyway. What I will do is I'm going to give this out to you. So this is in the handout section of Blackboard. And this might be, and y'all should have seen this in DC. I'm gonna talk to the DC Circuit because you probably know, so this is handouts and then standard resistors. So we said it was 49 something ohms. And of course we can't, this chart is set up for 5% and this 10%, but you can't even find 10% resistors anymore. So 49 ohms, that means I would come over here and I find here is 49. So here's 47 and 51. Which one would we use? Yeah, because if we go up, Zener current, we go towards the negative. If we go down, we go away from the negative. We're constantly trying to do that. So I'd say 47. And then I would come up and I calculated what? So the best value, which we can't choose, the best value would be 49 something. So I'm going to come up here, and this is a 5%, and I'm going to multiply my 47 by 1.05, which would raise it by 5%. If it comes up to be more than my calculated value, I'll round down again. Y'all understand that, yes or no? So so how did y'all calculate tolerances back in DC? You multiplied it by 0.5 and then you added that. Well, I learned a long time ago, you can multiply, if you want to go up, you can multiply it by 1.05. And if you want to go down by 5%, you multiply it by 0.95. And so the way y'all learned it was multiply it by 0.5 and then add it and then subtract it. So I'm going to take that 47 and I'm going to multiply it by 1.05. That's going to give me what the high end would be. So we'd go down one more resistor. Y'all understand that? Yes or no? So what do we calculate? So what do we calculate? 49 point what? So this is the absolute maximum. 49.5 is the absolute maximum. So we went down to 47, but it's got a 5% tolerance. I'm going to say times 0.105, and if it comes up to be larger than that, then I'm going to round down one more. So what's 47 times 1.05? So that would be close. I'd probably still go down one more. But it looks okay. So 47 ohms looks okay. So what we do when we calculate our first thing we're going to do is round it down to the next standard value, and then I'm going to check the tolerance. If the tolerance comes up greater than my calculated value, I'll round down one more. So 47 ohm looks okay. Now what I would do is I would see what is our maximum? What did we say our maximum was? It was 7 volts, right? You understand that? So what should that wattage of that resistor be? Remember, it's the maximum middle drop is what? 2 volts. So what would be the wattage rating of that resistor? V squared over R. What size resistor are you using? What's the standard sizes that we have? Anybody know? Standard wattage ratings for resistors? That's something else. So these actual lead resistors, we start off with an eighth of a watt, and then we go up to a quarter watt, then we go up to a half watt, then it goes to 1 watt, and then 2 watts, and then I think it jumps to 5 watts. So once it gets past there. So which one of these could we use? 1/8 watt, quarter watt, half watt, or 1 watt? Yeah, we could use 1/8 watt. We'd probably use quarter watt. Anybody know why? Yeah, they're like this. So they made quarter watts is made by the 1,000. Half 1/8 watts are not made. So it depends on size. If I was concerned with size, then I would use an 1/8 watt. If I wasn't concerned with size, I would use a quarter watt. Now let's check the Zener. So what's the maximum input voltage? So let's say I remove my load altogether. So right now I can come up here and I can unplug this power supply. So now my regulator is having to manage all that current, right? You understand that? I don't need that, girl. So what would be the maximum current flow through the Zener if I remove the load from my power supply? This is kind of like DC, right? So I calculate the maximum flow in my circuit. So the maximum flow we will allow in this circuit would be equal to 2 volts divided by 47 ohms. This is maximum current. So what's the maximum current? We've got something wrong there. Now, why I knew we did something wrong is that we designed this thing around getting 120 milliamps out of this thing. Yeah, but y'all see, I told y'all wrong. So it's my fault. You know, see where I made my mistake. No, it's not going to be 47. 47 wouldn't let 100 milliamps. So we're designed our load around 120 milliamps. And if we took 120 milliamps and multiplied it by 47, we'd see that's going to be way more than what we need. Can anybody see where I made a mistake on that? I see my mistake already. Huh?
Go back, take the minimum, vote divided by,
No, we don't. This is when we chose the resistor. We're not going to change. We chose the wrong side of it. Can anybody see what's wrong with this formula right here? So I just did that to see if I was catching. So the maximum voltage we're going to put over here is 7 volts. The minimum voltage we're going to put over here is 6 volts. So this resistor right here, which we're computing the size of that resistor, the maximum voltage it's going to drop is 2. The minimum voltage it's going to drop is 1. It will never, ever, ever, ever drop 6 volts. If it drops 6 volts, then there's nothing left for the zener. Okay, y'all understand that? So if I apply 6 volts and it drops 6 volts, how much voltage do we have left for the zener? Huh? 0. So, y'all might have to go back and edit my report. So, this is not supposed to be 6. This is supposed to be 1. Minimum voltage, the resistor will drop over the maximum current of the load. So I was using this to calculate this. This guy right here never sees 6 volts. It's either going to drop what? 1, 2, or it's going to drop 1.
In the real life scenario, you think for the item that all time all about that segment you have a kind of talk about her have all the items that you talk about that kind of
No, it's what you have unregular. So I would go out there on my car and I would run it wide open. I would measure the output. Then I would idle it and I'd measure the output, and that would give you your minimum and maximum. But we're not going to get 1,000 watts out of a zener. Zeners are used for low current, low wattage power supply regulators. What we'll find out is that even though I've got a low wattage device, so here's your TC. I looked at a let's see if they give us the electrical diagram on this. I got it somewhere where they actually give you the actual schematic on these regulators. And what you do is you would see a zener in there. So somehow we got to come up with a device where we can get more current than we get out of a zener. So zener is the basic element in just about all regulated power supplies. So later on, what we'll find out is we can come over here and so what we can find out later on is we'll come over here and do this. We'll take the output of this guy and we'll hook it up to one of these devices. Okay. So this will come over from here. And we'll do this. So right now, we're down on this guy, we're going to be getting milliamps out of the Zener. But once we figure out the Zener, then we can use it to control the other electronic devices that will give us a lot more current gain than the Zener. But if I was to look inside this, so then we could take this and put it inside an integrated circuit. And over here, this might be 2 amps at 5 volts. Even though down here, we're dealing with milliamps. So what we're doing is we're getting the basics of what we call a regulated IC. But you still run into these because these regulators, these 3-terminal regulators, they cost a lot of money. So if all I'm going to deal with is milliamps, then we'll use a Zener. If we need more, then odds are we'll go to what we call a 3-terminal regulator to get more current out of it. So did I answer your question, Mario? Okay. So what's on this side of the Zener? This is what we're giving the regulator. We control this. This is what we get out of our unregulated power supply, unregulated filter. So over here, we got to have unregulated filters. I wouldn't put pulsating DC into this thing because every time it dropped down below Zener, it would just clip off the top. So if I put unregulated DC in this thing, pulsating DC, then what we'd see is we'd see this. And the top would be clipped off, and then it would drop down, and the top would be clipped off, and then it would drop down. So if you ever see that on the output, you know that your filter's gone bad. So what we did, or what I did, y'all didn't do anything with it, is that when I calculated the minimum voltage, that is not the minimum voltage. The minimum voltage dropped by the resistance. So if I come over here and this is 5 volts, and then over here we're putting 7 through 6, and what would be the minimum voltage dropped by the resistance? The minimum voltage would be 1. So over here I would say, okay, my RS would be equal to 1 divided by, what do we say, maximum is 120 milli plus 1 milli. So if I put 6 volts in, and this is where I should have caught it, guys. If I put 6 volts in and I drop 6 volts right there, what's left over for the Zener? None, right? So that formula is the minimum voltage dropped by RS divided by 120 milli. So what size resistor would that be? So 8. Then I'd come up here and look at my resistor chart. If I didn't close it out. So there's no standard resistor, so this is a bad example. What's the smallest they have up there? 2.7 is the smallest they have up there. No, go ahead, guys.
No, I was trying to see what I was doing before, but I remember now.
Yeah. So this is our standard resistor. So the best we can do here is, I'm sorry, what did we choose? 8? So I would try a 5.7. Did we come up with 8 ohms? we came up with 8, right? 8 point something. Everybody okay there? And then I always round down, right? That means on my standard resistor chart, if I got close enough I can see it, I would choose a 7.5, and then I'd multiply that by 1 point, and I'd multiply that by 1.05. What does that come up to give me? 7 point what? So 8 would be right on 8, no, that would be over. So we chose a what? Oh, we calculated 8, so yeah, so that'd be okay. So 7.5, okay, and we started off with 100 milliamps here. I think we had 20 milliamps there. Yes, yes. I'll check it on your 7.5 ohms. This is L. Okay, so what would happen if I pull the load off? Disconnected load. And the input was 7 volts. So I mean, this guy right here, RS would be equal to 7 over 7.5. What would they give me? Yeah. So my Zener, VZ would be equal to 5 times 930 millirich. So that means I could use a 4700 series Zener here because they're rated at 1 watt. So that would decide what Zener you would actually use, right? Understand that? Yes or no? When there's no load, the load current is approximately 0. All the current flows through RS must go through the Zener. When there is connected load, RL, total current flowing through RS is shared between the load and the Zener. To keep the current through RS constant, as RL is decreased, the load current goes up and Zener current goes down. So choosing the size of that resistor is very, very, very important. Okay, so we looked at this, right? So 1N4728. Now get out the data sheet and let's see if we can find this stuff. So 1N4728, what's the Zener voltage? Everybody agree with that? What's the Zener test current? Everybody agree with that? What's the knee current? What's the wattage rating? What's that? What's the maximum current? What's IZ max? Can't find that on data sheet. Now this you gotta calculate. So we take 1 watt divided by 3.3 volts. What's that? 303 watts. We're calculating IZ max. And what we're using is taking this formula, power is equal to V times I, and we're rearranging it to solve for I. So we're using P over V. So IZ max would be equal to P, which is 1 watt, divided by 3.3 volts. And we're calculating for current. So what'd y'all get? 300 what? What's that? Yeah, there you go. 303. Okay, so which zener would you use if you were looking for a 10 volt zener? Now we're looking for a part number. So what would be the part number you would use on that chart if you needed a 10 volt regulator? Good. And what's the need current on that? Yeah, IZK. Turn 50 micrograms, right? And you got to understand to limit the number of ranges, data sheets do not use legal engineering notation because they don't want to jump between charts. So as soon as they label that top one milliamps, then they didn't want to go from milliamps to microamps, right? You understand that? Okay, what's the zener test current? What's that? 25. And what would be the maximum current? IZ max. The zener voltage, 1 divided by 10. So notice on this guy, they're all rated at 1 amp, so as the zener voltage goes up, then the maximum current goes down. Everybody on those? Okay. So that's a lot of stuff in that data sheet, but we can design a zener regulated power supply without using very much. In fact, we don't even use IZT. It's just as important, IZT is where the zener voltage is established at a certain temperature. What's the temperature rating of this thing, by the way? Y'all see anything on these data sheets on the actual temperature all these ratings are made at? That's probably maximum. Let's see. It should be at the very top. Like 100. Usually it's around 25 centigrade is pretty standard for solid state. So here's all those fancy formulas, by the way. So VRS max, basically this is DC. These are all Kirchhoff's laws. So the voltage drop, the maximum voltage drop across the series resistor would be your VN max minus your zener voltage. Your minimum voltage drop across your resistor would be VN minimum minus your zener voltage. So your RS is VRS minimum, not VN minimum, VRS minimum, divided by I of the load maximum plus IZK. Always do what? Round down, and I should put it out there and check your tolerance, right? Always round down and check tolerance. Now, of course, all ours are going to be 5%, so that means you'll just multiply by 0.05. And if it comes up to be greater than what you calculate up here, then that means you need to round down one more. Power dissipated by the resistor, V squared, RS max squared divided by RS, so V squared over R. Or if you know the current, to me it's easier to do the voltage because the voltage is in your math, right? So what it does is, if you know V squared over R, then it's going to save you having to calculate current. RS max equals VRS max divided by RS. VZ max, IZ max equals IRS max minus minimum load. And then the power of the zener would be the voltage divided by the maximum current flow through the zener. Now, where did you learn all these formulas at? You learned them in DC. All these formulas are DC formulas. We're just adapting them to zener power supply. Here's Kirchhoff's law right here. Here's Kirchhoff's law. Here's Ohm's law. R is equal V over I. Here's power, V squared over R. Here's I, V over R. Here's maximum. This is using Kirchhoff's current law, right? And then this is your power formula. That's V times I. That's the easy one. Every one of these formulas you learn in DC. But all we're doing is applying it to what is V, what is R, what is I. So we're trying to figure that. And what we're dealing with here in DC, you was dealing with something that was static. And these zeners actually changed their opposition. They literally dynamically change their opposition to try to maintain a constant output across their, once you break them over. You don't do it, it does it automatically. And all we got to do is choose the right resistor. Once we choose the right resistor, we make sure we're not going to burn anything up with that resistor, right? It should be in your data sheet. That's under Zener power supply. So let's see. Let's look under there and see if y'all see that. So in your I'm not in your data sheet, in your formula sheet. So there should be a section under Zeners. Zeners. We're looking for VRS max. So writing down the formulas is good, but what you need to do is figure out how to find them on that formula sheet, right? Because you can't use your notes in a test. You can use that data. You can use that formula sheet on test. So do y'all see all these? By the way, this is another sign for multiplication. Normally when we got in algebra we don't use the x for multiplication because x could be a variable, right? So all these charts, of course, did I put the tolerance in there? Checking the tolerance, is that on there? Check tolerance. Of course, this is going to vary with our resistors, but standard resistors, by the way, is all the ones that we have are 5%. And so these are all 3-band resistors, 4-band resistors. 5-band resistors get into your less than 5%. I forgot to put my list on there. I've got it up in front. Sorry you're gonna run into these, yeah, and this bothers me too. So I come over here and I'm teaching, programmable control. And they're showing us the makeup of, an input port. And this is in the textbook. So don't take for granted everything you see in textbooks. So if you know better, then, let's see if I can find that. Where they actually show the wiring of one of the input ports on a PLC. I'll have to find that. You know, what they do is they come in with a Zener and they don't put a series resistor in. So what would happen if they didn't have the series resistor in the Zener? It might be in this one. Oh yeah. Well, what's wrong with this? So this is a textbook. So this is bringing AC in. So they're bringing in AC. This is actually inside the PLC right here. They're coming through a rectifier. And then what's wrong with this? Well, it's supposed to be between it somewhere. Gotta have a, yeah, this sucker was, if this was the way that circuit was wired, it would burn up in a heartbeat. So over here I want 5 volts. Over here I got 120 volts. And so anything over 5 volts would be a short circuit. So we either got to put that series resistor down here, or we got to put it somewhere else. So this guy right here drew this, and there ain't no way in the world somewhere. So you got books that actually give out wrong information. So this would probably be okay. I wouldn't think the Zener would be in series. This would definitely be wrong. And of course I show that to my class. So you actually look at the people that knows what's going on. They'll put a resistor in. So usually inside the PLC operates on 5 volts, but we can put in a lot bigger voltages into these things than we need. The standard now, by the way, you won't hardly see 24 volts is pretty standard. So we got 5 volts right here. We got 24 volts over there. So what they do is they just put a Zener in there and they just flip it down to 24, from 5 volts to 24 volts. This is what we call an optical isolator. And what it does is it isolates the actual input coming in from some machine or something. It isolates it from the electronics that's inside the PLC. So we're actually passing information through this thing with light. And we'll look at sensors. So some of the sensors we'll look at, well, they call them transducers in this business. So sometimes even books make mistakes, you know, on the way they hook stuff up. But if you understand how things will work, you know that can't be right. And would I write the publisher about it? No, it just gives you a good example of what's going on. And we'll go ahead. So the next lab, once y'all get through with the lab, y'all do an unregulated power supply, then, but you're adding filters to it, right? And we're not, by the way, filters, you should expect an output voltage slightly less than V peak out. It's not going to be the same. It's going to be slightly less. So that's something you should think about when you're doing your lab, and they want you to measure the ripple voltage, and you'll notice that the output voltage jumps up to almost V peak out. Okay, guys. So what time is it? We're gonna have to go in there. Let's see if y'all can. So what size resistor would I use? You're using a 1N4747. The input's going to be 30 volts plus minus 10%. So what would that be right off of that? So what would the maximum input voltage be? What's 10%? Be 33 would be maximum. Minimum would be 27. So what size resistor would I use? It's a 1N4747, and the load current is going to be 10 milliamps or 20 milliamps. So another problem I had was I chose 100 milliamps for a Zener, which is not good. What do you mean? What do you mean? Turn around, Jess. Don't see your face now. No, I don't mean, I told turn around and let the class see your face now. So what was you asking? First of all,
Okay, you add 2 milliamps, which you're making that perfect. Then you're going to divide the voltage into that. And
no, what we're going to do is first of all, we're going to go through the formula. So first thing I needed to figure is I needed to figure VN max. These are all DC, by the way. So we're already DC when we get here, right? And then I needed to try to figure out VN minimum. So I multiply this times 0.1. So that, if I multiply this by 10, by 0.1, that gives me 3 volts. So then my maximum would be 33 volts, and my minimum would be 27. You okay? See how we got that? Now, the next thing I need to do is before I start, I need to look up a 4747, and I need to find IZK. Not mid, it must be micro. Milliamps. It's micro. Yeah, that would be a lot of current for a Zener. Okay, so now I've got everything I need to calculate the size of that resistor. So Mario's already got 1.1K. So, I'm sorry, we need VZ. What's VZ for this? We gotta have that, guys. I'm sorry. Zener voltage for 1N4747. What's that? 20. So we're trying to calculate RS. So what voltage are we going to? Well, let's calculate DRS, and it makes it easier. Maximum and DRS minimum. So what would be the maximum voltage RS would have to drop? What's that? would be the minimum voltage RF would have to drop? Have we lost anybody? Everybody okay? What's that? So what we did is that this is what we're bringing in. This is what we're getting out. And what's between what we're getting in and getting out is that resistor. So what we have is we're going to hook up this circuit right here. And then we've got a load out here that it could be a resistor, it could be a light bulb. We'll use a resistor right now. It's going to be 20 volts. And its current is going to be between 10 milliamps and 20 milliamps. Okay? So, what we're trying to do is we're trying to figure out what voltage this resistor is going to have to drop. The maximum it would ever have to drop would be 13 volts, which is the difference between 33 and 20. The minimum it'd have to drop would be 7 when the input is at 27 volts. Okay. So I want my resistor to drop the minimum voltage at the maximum load current plus IZK. So RS calculated, so I'm going to put calculated because this is not the one, we'll never use this guy. We'll never use that. This is just giving us a shot at what we're going to use, right? So what's my minimum voltage you'll ever drop? 7. What's the maximum current? What's the maximum current? 20 milli plus 250 micro. Now what we're adding IZK to this is that the worst situation we will have 250 microns flow through this. We're actually going to have more than that. So what would be our calculated size for RS? Or 25 ohms. Okay, 26. Thank you. So what do we do on Zingers with that? We always round down, right? Okay, then we need the chart. There should be a chart in your data book. Should be towards the front. Okay, so I say 24. So we cannot do that. So I'm going to say 24 times 1.05. What does that come up and give me? 25.2, so 26 is fine. 24. Oh, I thought 26 is what we can't do. 24 is what we can. What's that? Yes. If my percentage comes up to be greater than or equal to or greater than that, I will round down one more resistance. I didn't get 26 up. Plus 207. What 207? Oops. I need to get rid of this guy. 25 micro, 250 micro. 20 milli plus 250 micro.
Oh, that's micro. Okay,
Yeah.
I got that one.
That's okay. I never make mistakes. Y'all know that, right?
Yeah, it's like 25 rather than 25, 26. So, let's see, 26, so that's 24.
20, is everybody okay? Y'all listen to Mario, y'all need to be doing this yourself, right?
24 feet long, and 24 long.
Does everybody agree with that? Yes, no? Yeah, so, so here's my calculator, right? So I've lost all my stuff that I wrote down before. So what's our minimum voltage? 7. Divided by, you're gonna have to open up parentheses, guys. Open up my parentheses. What's our maximum current? Now what's our maximum load current?
20.
Okay, 20 milliamps, right? Plus, I've opened up parentheses. Plus, yeah, we could do microamps. We could do plus, we could say 0.00025, right? Or you could use your engineering notation on your calculator. So it's up to you. Most of these millis and micros now, I see the number, and to me it's just easier to enter it than to look for use the exponent. Close this, it equals, and I got 345 ohms. So I'll say that again. So let's use, so 7, we're okay there, that's the minimum voltage. Then I'm going to say divided by, I'm going to open up parentheses, and then I'm going to say 20 milli, so that would, if you're using the engineering notation, 20 times 10, mine's called EXE, some of y'all have X, and then I would say minus 3, then I would say plus 250 times 10 to the minus 6. We'll close my parentheses and hit it. We might have to. Yeah, but let's get this one out of the way right now. You're probably exactly right. So we start off with the minimum voltage, right? And then we say divide by. Now, if you need to use the powers of 10 or E to the E or EX, some of them's EE, some of them's EXP, some of them's EX. Some of the calculators have a times and then they have a 10 raised to it. So you have to find that key. But you're going to have to open up parentheses. You got to do parentheses because if you don't, you're going to lose off one of your numbers, right? And then I'd say my minimum current, so I'd say my maximum current, 20. And then I'd say this is my key times 10 to the minus third plus 250 times 10 to the minus 6, close my parentheses, and I should be able to hit equal, and it should give me the answer. But like I said, you see how long it took me to hit EE and enter all that stuff? So that's what I'm saying. I've been at this so long that I actually see the fraction. So when I saw 20, I saw 0.02. That was in my head. And it's easier, if you understand that, it's actually easier to enter the fraction than to use the power key. So 345 ohms, we'll round that right down. So Mario's already did that, 345 ohms. This is our calculated, right? So our calculated is 345 ohms. So this is RS calculated, 345 ohms. 45 each. Okay, but what are we gonna use? So we'll find 345, we'll find the next lower thing below 345 in the chart. So what's the next lowest thing? Okay, 330. And I'm gonna take 330, I don't even need, I'm gonna multiply it by 1.05. What does that come up giving? 346. So that means this is out the window. Because we came up more. It could be more. Odds are okay. So I'd go one more down. What's one more down? 300. So I'd use a 300 ohm resistor. Round down, check the tolerance. If when you check the tolerance, if it comes up to be greater than what you calculated, then you need to round down one more. But what we're trying to do is we're trying to get this thing to move this way. We don't want to move it that way. We want to move it this way. If we move it that way, we're moving towards the negative. Okay, so what wattage rating should that resistor be? So we already compensated for the 5%. We already taken care of 5%. So 5%. So what's the maximum voltage? This is where we're going to use VRS maximum. What's the maximum voltage it will ever drop? What's that? 13 volts. I'm going to square that, and I'm going to divide that by R. V squared over R. Oops, no, we chose 300, right? This is not what you calculated. You're calculating the power needed by the resistor that you're using. So I'd have to use a 1 watt resistor then. There's no such thing as a 563, so we use a 1 watt. What about my Zener? 1N4747 is rated at 1 watt. Are we going to burn that thing up? Or do we need to go to another type of Zener? So when would the current flow through the Zener be maximum? So I'm going to say power through the Zener would be equal. I know the voltage is going to be VZ. What's the current? Times I. This is going to be the maximum current that will flow through the Zener for the circuit, not IZ max. Somebody help me out. So I'm going to take somebody help me out. Okay, 20 volts. Oh, yeah, we're looking for IZ max. No, we're not looking for that. We're looking for if we exceed my Z max, we're gonna burn it out. So I know VZ. What's the voltage rating on there? So power of the Zener is going to be, what's our voltage rating? Huh? What's our voltage rating? What's the Zener voltage? Okay, 20. So I know power is equal to V times I, so we know it's going to drop 20 volts. So now we're trying to figure out when the current flow through the Zener will be at its maximum. So I've got this circuit right here. And then I've got a load over here that's pulling between 10 milliamps and 20 milliamps. I know this resistor, I know my maximum voltage over here is 30 volts, 33 volts. I know this resistor right here, the maximum that it's going to drop is 17 volts, right? 13 volts. I know the size of that resistor, so I can calculate the maximum current flow through R. So I max through my resistor would be equal to 13 divided by 300. Okay. So this gives me the maximum current flow in the circuit. Okay, 43 milliamps. Not yet, because that's not what's flowing through the Zener. The worst case scenario would be if this guy here, so if the load current goes up, Zener current goes down. If the load current goes down, Zener current goes up. So what I would do to figure the maximum current flow through the circuit is I would take this 43 milli and I would subtract 10 milli from that. And then that would give me, so I'm taking VRS max divided by RS, and then I'm subtracting I the load minimum. And that's the way I'd figure that current. So what are we using here? Well, we're using Kirchhoff's current law. It says if I know the current flow in a current circuit, and I know that load is pulling 10 milliamps, then I know the Zener's got to be conducting the rest of it, right? You understand? So we just calculate, so what would be the wattage rating of the Zener? So I would say what? So power in the Zener would be equal to 10 volts. I'm sorry, 20 volts. So 20 volts Zener, y'all watching. 20 times, and then I would say 43 milli minus 10. So what's 43 milli minus 10? 13. What would that power be? So is my Zener okay? Would it work in this circuit? Will we burn my Zener up? Yes, no. What's the Zener, what's these rated, all these Zeners rated at? 1 watt, 640 milliwatts would be fine. 30 volts, load between current, 20 volts, 20 to 10 milliamps, 27 volts, 300 ohm resistor. Y'all get great on that. Zener, 667 milliwatts. Y'all calculated that. Y'all did great. So, you designed your first Zener regulated power supply. All the formulas, every formula is what you learned back in DC. And there's very few formulas we're going to learn from scratch in this class. We're going to take what you learned in DC and then we're going to apply it to solid state devices. All you got to do is figure out what V is and what I is, right? And what P is, how to calculate V times I. So what formula did we use then? Well, we said PZ is equal to VZ times IZ, but what we had to do is we had to calculate IZ from the circuit. We know Kirchhoff's current law. We use Kirchhoff's current law. So what I did is I calculated the maximum current flow we could have for that resistor, and then I knew that current was shared between the zeniths. And what we're trying to do is figure out when the Zener current is maximum. Well, we know if this current goes down, this current right here goes up. So that's what we did. We subtracted this, right? You understand, from what flowed through the resistor, and that gave me my Zener current. Then we need VZ because it was given. We multiplied it times IZ, and then that gave us the power. If it would have came up to be greater than 1 watt, what would that tell you had to do? You could not use a 1N4747. You'd have to get on the internet and find a Zener you'd have to find you a 2 watt Zener, right? Or whatever is required. But you have to start somewhere, right? You understand that? So great job. To me, these are just laws that you should have learned in DC. If you didn't learn those laws in DC, then you're going to have problems with solid state. And I know DC wasn't good for some of y'all, because what was it? It was virtual, but you still should have had to solve, whoever taught y'all should still have had y'all solve those circuits and learn those laws. Well, here you don't even have to learn them. You know, all we did, I know the law, so I went through it, but you got the formula sheet there, right? You understand that? It should have said PZ is equal to VZ times IR max divided by minus I of the load minimum. That formula should be on your formula. But mathematically, I don't know. You thought with the formula sheet. Okay, guys, see y'all Thursday. If y'all don't have any questions, put my data books up. By the way, wipe down your seat for me. Yeah, what we'll do is we'll start doing lectures online, and then if you don't get back in before the end of the semester, what we'll do is you'll take tests and everything, but you're gonna have to have a webcam, right? And a microphone, because I'll have to proctor the test. At the end of the semester, we'll give you an incomplete in the past, and we'll arrange